Hello, welcome back. Happy April Fool's Day. I'm afraid I was not clever enough to plan any April Fool's jokes for you today, but life goes on. Hello, 17 bright-eyed and bushy-tailed students out there. When we last left our heroes, we were talking about Bohr and Einstein's contributions. Oh, Hunter, hello. Sam, hello. Emily, hello. Nice to see you guys. Hello, Sharon. Hello. I just put your empirical molecular formula tests into Tyler. Feel free to look now if you want to, I guess. But I did give you, again, scores were strong. I mean, most people did really well. What I went ahead and did was I went ahead and gave you like a pandemic curve. So I went ahead and gave, even though it messes up my numbers, I pushed my comfort zone. I went ahead and gave you guys a 2-point curve, like a 10% curve. So it's in the grade book out of 18 points, not 20 points. So so there you go. So if you did better than an 18 out of 20, then your grade went up a lot. So hopefully that helps. Yeah, they were great. Did a nice job. Sorry it took me so long to get them in there. Hello, Emily. Hello, Maddie. Hello, my elites here. And so what we're going to do today is I'm actually going to really push my comfort zone a little bit. We're going to talk about a topic that I've meant to talk about for a couple years, but now since I have a little bit of time, we're going to dig a little deeper into where bright line spectrums come from. So this is a new lesson for me today, but I think you'll like it. Again, don't worry too much about the math here. This is more of a conceptual appreciation of it. And again, for the high flyers, you'll be able to dig a little deeper on your own, just like all this stuff with modern atomic theory. Hello, Abby. Hello, Noah. Hello, guys. Hello. So housekeeping stuff. We do have, let's see what we got here. The quarter, I sent out an announcement yesterday. I'm going to end the quarter. I'm going to kind of stop stuff this Friday. Technically, they extended it until Monday or Tuesday, the April 7th. There's really, again, instead of like trying to shoehorn in those last 2 days, stuff that's due by this Friday will go in the third quarter, and anything after that will just start building onto the fourth quarter. The fourth quarter is going to be lean on points anyway, it looks like, considering now I guess we'll be doing this for the next entire month. So into May, I guess we will be now remote learning. So you'll forget what I look like, and you'll just remember this guy right here. This is all you're going to remember. The Muppet version of Mr. Amical. And so if you have any questions about your grades, again, email me. Not a big deal. Sam, you should give extra credit to the people who are at the class. Yeah, I thought about that, but I think you guys, there will be a certain natural consequence at some point for the people who aren't doing much for the class right now. And if they're not here, maybe they have a good reason. Maybe they're helping out with family things. We're all fighting our own battles nowadays. So I don't want to punish anybody who can't make the live lesson. I'm assuming they're doing something good or sewing masks for doctors or nurses or something. So I won't judge their lack of attendance. What else? I did one of your high flyers also, one of your peers sent me their stoichiometry assessment, and it's pretty much exactly what I would expect. They did it on paper, they took pictures, and then they put it in a Google Doc in sections. So it was really easy for me to follow their work. They knew they had everything. It was fantastic. So I asked permission, and I copied that, and I shared it with the rest of you. So I use that as a guide. Again, the lesson on Monday, you can use as a guide. You can watch me walk through one problem. You can see what that student did as another example of what to do. I also started time stamping the videos. So I did Monday and Tuesday's video. I put timestamps. So if you want to see a specific part of the problem, you can then go and look there and just timestamp to that part of stoichiometry. No one has asked me any really questions about their stoichiometry problems outside of just formatting issues. So I'm assuming everybody's doing okay with that. So that's due on Friday. I don't know if that's going to make it onto the third quarter or not. I doubt it. I'll probably wrap stuff up. All right. And then again, Abby in the audience there. This is a shout out to Abby here. I did finally, Abby said that she checked out the Flynn live lab and she enjoyed it. So I popped in yesterday and it was good. It was good. It was fun. There was sort of a morning DJ sort of vibe to it. There's this one person, and then he had like a sidekick who doesn't know much about chemistry, who was helping out with the technical stuff. And they had lots of interactive quizzes and lots of videos. It's a little rough around the corners, but I appreciate the effort, and it's perfect for you guys. It's really, I think if you watch it, I think it's going to validate a lot of what you've learned this year, and you're going to feel pretty good about yourself. And if you don't know it, then it's something you can learn. So I'm giving my seal of approval to the Flynn Live Labs. I enjoyed it. Thank you, Abby, for pointing it out to me. I had a good time. I enjoyed answering the questions. I got them all right. I'm really proud of myself. So check it out today. It's good. It's good. It's not below you, and it's not above you. It's meant for you. So a shout out to Abby there. Thank you, Abby, in the chat. All right. So anyways, let's go on to today's ambitious lesson. I am going to show you. I promised I was going to do kind of a sort of a non-mathematical view of modern atomic theory. So I'm still going to do that. I'm going to show you some of the equations that are backing this up. As I said before, remember that this is the math is the coding language of the modern atomic theory. So if you don't want to do the math, that's totally fine. But don't get frustrated if you don't completely understand it. That's going to be part and parcel. Just like if you don't want to learn how to code, that's fine, but don't be upset when you can't really do much when you're trying to make an app, So the math is the operating language of the modern atomic view of the atom. And we'll get more into that tomorrow with some of the I call them the three wise men. But what I'm going to do today is kind of show you where bright line spectrums come from. This is advanced. This isn't in the video, but I thought it'd be a treat so that you guys can kind of see where we're getting this stuff. I was excited to dig a little deeper, but again, don't worry about the math. For those of you who love math, feel free to dig in and see where they got this stuff, but it is what it is. So let's go back to the whole idea of where spectral lines came from, bright line spectrums. Again, we talked about this all the way back when we talked about where elements came from. People have been getting rainbows out of prisms for millennia. That goes all the way back to the Romans, and so it didn't take long for people to realize that when you heat up certain substances, they give off different colors of light. And so people have been studying the emissions. Oh, hello, Will. How you doing? People have been studying the emissions. I think Alex popped in too. And so I won't say, I won't say anything about Alex. Alex, you know Alex. Thank you. Anyway, so people have been studying the spectrums of materials for centuries. And so this got serious, this got real, as the kids say, in the late 1860s when they developed the spectroscope. We've talked about the spectroscope before with the idea that, you essentially heat up a pure substance and then the light goes through, breaks up in the prism, and then you can see the bright line spectrum. To see a bright line spectrum from emissions, you have to heat something up until it gives off light, and then you break up that light with a prism or diffraction grating. And they got really good at it. We talked about some other people. Who were some of the other people we talked about that I'm drawing a blank? But there were people that were also big into photography that also did a lot about real. Swan was one of them. Who was the photographer? Oh, that bums me out. I'll remember at some point during the presentation. Anyway, so we had these bright line spectrums, but no one really knew where they came from. It was kind of weird. Like, where was this stuff coming from? And so along came Balmer and Rydberg. Balmer was a Swiss school teacher and also a mathematician. And he mathematically came up with a way of getting the spectrums for hydrogen. So he came up with an equation, and there it is there. Don't worry about it. But he figured out a mathematical puzzle that got him the wavelengths when he put in numbers like 1 and 2 for M and N and stuff like that. So he put in very simple numbers. He figured out a constant, that's B, and he was able to get the lines for hydrogen. Now again, this was just like this was a mathematical puzzle. So it wasn't like he knew what was going on. He just figured out the mathematical puzzle of it. And a little bit later, a guy named Rydberg produced a more inclusive formula. He was studying the spectrum of alkali metals, and then he realized that Balmer's work with hydrogen was really just a special subset of his own equation, which was really pretty cool. So there was some validation, multiple lines of evidence showing that this stuff was working out. Now again, I wouldn't worry too much about those equations. understand that, again, we're looking at, he was kind of populating with numbers. There were constants. R is considered the Rydberg constant. Again, you don't have to do any of this or know any of this. But oftentimes, as you'll see later in chemistry and before, sometimes we need a constant to make something that's proportional actually work out to a number. We saw this with energy, right? Energy is proportional to frequency. Well, when we put in Planck's constant, then we got an equation. Same thing later in the year, we're going to do gas laws. We have this gas constant, the proportionality constant, which changes stuff from being just proportional to actually being mathematical values. So that's the purpose of constants. All right? So that's what Rydberg did, is he came up with a more inclusive equation. So what did Bohr do? All right, so now I'm going to try to tie these guys into what Bohr did. So what Bohr did is, remember, Bohr came up with a revised view of Rutherford's model of the atom. And you can check yesterday's lesson if you want to. Now, up until Bohr, there was no explanation for this math, right? They just kind of figured out a mathematical puzzle and said, well, that's okay. We found an equation for this, but we don't know where any of these numbers are coming from. Well, Bohr ran with this, and he actually took the equation and incorporated it into his model, right? Remember the model we talked about yesterday, where there are energy levels where electrons can live, right? And they orbit without losing energy, and they can transition from radii to radii by emitting or absorbing energy. And so when he took this concept and then he applied the Rydberg equation to it, he was actually able to show that this stuff all was related, right? These equations made sense when you plugged in stuff like wavelength and Planck's constant and energy. And I'm going to do a little mathematical derivation for you just to show you, right? We have, again, up here, this is called the wave number, by the way. It's just the inverse of the wavelength. And that's what Rydberg was using. Well, again, how do we get that down to what Bohr realized was energy, right? Just to show you some derivations here. And again, this is something you should be able to do, but we're not going to have you do it. But I'll just show you that. Remember, so we know that C equals, frequency, lambda times frequency, right? And so we can isolate this if we want to, and we can change this to 1 over lambda, right, equals nu C. And I'll let you figure out how I did that, right? So I can figure out this part of it here, okay? And then I can also say, okay, well, energy, remember what Planck said, energy equals Planck's constant times nu. And again, we can isolate and solve for V, right? We can say frequency equals E over H. Well, watch this, right? We can take this and plug it into here, right? And so we can end up changing 1 over lambda to E over HC. All right, now you might not, you're like, okay, why do I care? Because remember what we said, if we cut out these constants, what do we got? We knew that the inverse of wavelength was proportional to energy, right? So what Bohr did was he showed, okay, we can actually tie all this stuff together. We already have Planck's constant. Remember, Planck didn't even like Planck's constant, and now we just keep showing it. It's cropping up everywhere. Planck's constant ends up being one of these fundamental ideas of the entire universe. And so this was the big deal about what Bohr did. All right, so let me show you again some pictures of this. Now, again, don't worry about the math of this, but here's what was going on. Okay, so Bohr said that there were energy levels, and N1, 2, 3, 4, 5, 6. We really don't have to worry about going beyond 6. Now, that one electron in hydrogen starts here in what's called the ground state. And I forgot to write that in a slide, but the ground state is the lowest energy that an electron can have. And when it gains energy, it can pop up to other energy levels. All right, and then it can fall down all these different things. So it can jump up 1, fall down 2. Like there's all these places the electron can jump around in here. Well, some of these transitions are just right. We're talking about the Goldilocks thing here. So conceptually, this is what I really want you to take away from this, is as hydrogen's electron is bouncing around inside these allowed regions of space, right? It's got to gain energy or lose energy. Well, depending on how far it falls, it's going to be giving off different energy in different wavelengths. If no matter where it falls, if it falls all the way back to the first energy level, it ends up giving off so much energy that we don't see it. It gives off in the ultraviolet. And so a lot of these transitions we don't see. Now, again, if we detect them in the ultraviolet, we can see them in the ultraviolet, which is really cool, but we don't see any of these spectrums for hydrogen. And the same again, so we got too hot and we got too cold down here. if they drop back to the third energy level, any of these transitions don't give off much energy at all, and so they end up being in the infrared part. But then we get to the Goldilocks transitions. Any of these transitions where the electron falls back down to the second energy level, these transitions end up giving off wavelengths that are in the visible spectrum. And so that's where these bright lines come from. And that's really the key of all of this that I'm trying to show you guys, is that I've been talking about bright line spectrums all year. It turns out that Bohr realized that the transitions of electrons back down to the second energy level ended up dropping with just the right amount of energy that the wavelengths and frequencies were in the visible spectrum. And so they correlated to these 4 specific lines, right? And so you can see right there, again, the shortest drop right here gave off the least amount of energy. That's why it's red. And the longest drop here, look at this giant drop here, gave off the highest amount of energy, which would be purple. And that's the cool thing about this. Bohr was able to take that equation that no one really understood and say, you know what, I can make sense of this very easily if I, incorporate some of these ideas of Planck and discrete energy. And so in tribute to Johann Balmer, they actually called the visible lines the Balmer spectrum, or the Balmer series of the electromagnetic spectrum, which is really cool. Now I'm going to show you another picture of this. Now the problem with this picture, again, every picture is going to have compromises. The problem with this picture is, notice that it shows all the distances the same, right? That's not really how this works, right? I'm going to show you another picture that's got more information, but it's still really cool. This is a better idea of what's going on. You can ignore all these numbers. Don't worry about this. But notice that when these electrons are transitioning, this is a really cool kind of picture to show that the closer you get to this lowest energy level, right? Notice how big of a drop this is, right? And then the drops get less and less and less and less into essentially infinity, right? It doesn't take very long past n equals 5 or 6 that these energy levels get so close together that, it doesn't really matter how far away it is. You can actually calculate, in essence, how much energy it takes to remove the electron completely from the atom. And so what I like about this drawing is, I think you guys could probably understand, is that here is that first energy level, the ground state of hydrogen's electron. And notice how much farther it is to get to n equals 2. And that's why if that electron drops back down to the first energy level, this is giving off a tremendous amount of energy, which we don't see in the visible spectrum. That energy is in the ultraviolet. But if the electrons drop down to that second energy level, many of these transitions can be seen in the visible range. And that's where bright line spectrums come from. All right, if you're dropping to 3 or 4 or 5, again, it's even less energy, and these are all in the infrared. We can detect these with infrared, but we can't see these visually. And so Bohr came up with a way of explaining bright line spectrums very effectively. His model was very quickly adopted because it explained a lot of what people were seeing, and it made sense. And he didn't have to go into quantum explanations either. Again, remember, Bohr was not a big fan of how Einstein looked at quantum mechanics. Right? He was uncomfortable with photons for a long time. He decided to use quantized and discrete energy and try to explain it classically. Again, there continued to be a giant fight in quantum mechanics. It is still not completely resolved. But this is really, really, really cool. So anyway, this is not in the videos, but this is where bright line spectrums come from. And you can imagine that this should continue on for more complex atoms than hydrogen. Right? Now, each atom is going to have a different nuclear pool, and these steps are going to be different, and therefore they have different numbers of electrons. They're all jumping around different places. So every element ends up getting that unique spectrum of certain drops, emissions that are in the visible range. Now, again, I want to clarify that I used to say that the electron is sort of can't exist in between these, that it's teleporting. I've done some more research and stuff. That's not correct technically. I'm not the only one who's made that mistake. But the electron does transition very quickly within nanoseconds. And the electron itself can't even really be thought of as a traditional particle anymore anyway. And so it doesn't really make sense to try to visualize electrons like this. So anyway, why was this a big deal? Let's just summarize here. Why was Bohr a legend here? Again, Bohr's model of the atom finally gave a theoretical explanation to bright lines, which we had been looking at for a century. And that's probably, I think, Bohr's biggest accomplishment by taking the progress of Planck and Einstein and things like that, and Rutherford. He was able to explain bright line spectrums. And he showed where this mysterious equation came from. Remember that these people just kind of came up with these constants. And Bohr said, well, let me show you where you're getting that constant. So Bohr was able to, with energy and wavelength, derive the constants and say, here's where it is. This is that constant that you uncovered. I'll show you where we got it, which was super cool, right? And here's the most important thing about science, I think, is your ability to predict future behavior. If you think you have discovered something, predict something. Show me something that your theory or your hypothesis, show me something that your idea will predict before we've seen it. Right. And this is a great way of getting rid of like pseudoscience and stuff, is the idea of saying, okay, you've got a scientific idea, predict something. Right. Show me something that's going to be a ramification of what you're saying that we can go in and measure, and the great ideas centralize science, right? And say, look, it's all the same sort of thing. And so Bohr was able to predict, again, on that last slide, Bohr was able to predict, let's go back to the last slide real quick. Bohr was able to predict all of these transitions, Bohr was able to nail. Right? He was able to just say, okay, watch. And he just cranked out the equations and everything made sense. So that's why Bohr's model of the atom, though it was flawed and it was eventually overcome with a more complex math that we'll talk about tomorrow, you can't fault Bohr for really getting us the next step along the way. I will neither confirm or deny, chat, by the way, the source of that excellent student problem. That's why I bit my tongue in the chat there. So I hope you guys appreciated. I kind of stretched out a little bit there. Don't worry about any of the math. Just understand that, this is how it jumps around. So please ask some. I'll take a couple. Oh, whoops. Why was that big? Sorry for the typo there. Okay, so we have a question in the chat. That is an excellent question. Yeah. So the electrons are in what are called the ground state. They're as close to the nucleus as they can be based on where they're allowed to be. Right. And so when you juice up an electron, either through collisions or with energy, those electrons will transition up to higher energy. Right. So they'll jump up to the 2 or the 3 or the 4. Right. But what goes up must come down. Right. And so eventually that electron has to release the energy it absorbed, and it drops back down, maybe 1 step, maybe 2 step, maybe all the way back down. And so we put energy into the electron to make it jump up to the higher energy levels. And that electron itself will come back down. Just like a kid climbing up a slide, they're eventually going to have to slide back down. And so depending on how that electron drops, if it drops back to the 1 or the 2 or the 3, it's going to give off a certain energy because of the distance. And with that energy comes a certain wavelength. So all of these electrons, when they drop back down, they must release energy in the form of photons. Some of those photons we can see, hence the bright line spectrum, and some we can't see. And that's where we get into the spectrum, like the Lyman or the Passion, the lines in the ultraviolet or infrared. That was an excellent question. So we only see bright line spectrums when we excite atoms and drive those electrons up, and then they all start bouncing around. And those transitions, some of them, will give off just the right amount of energy that we can see them as a bright line. That was a great question. Other questions. Go ahead. If you have any other questions, throw them in the chat. Meanwhile, I guess that's all we're going to cover today. I was going to cover de Broglie, however you want to butcher his name. But I decided this is enough for today. This is enough. So I'll wait for some more questions. And then we'll do art improv and we'll call it a day. We don't have to, we can keep it a little light. We'll keep it a little light. So thank you for that excellent question. If you guys have other questions, ask them in the comments or the Google Hangout or email me, and I will get back to you. So I'm ready for art improv. Let's go. I've heard today's a good day for April Fool's jokes. So hopefully you've got some good pranks planned. A cactus and a guitar. Okay. I can combo those. I can do that. I can do that. Marin, we're on the same page. Yeah, so I can do that. Okay, so here we go. I can improv I can do this. This is definitely within my skill set here. All right. So we'll draw a cactus. Maybe I'll change the color. Hold on. Here now I'm really pushing it here. Pointer options, pen color. Let's make it green. All right, here we go. So we'll do I don't know how to rate. There we go. So we'll do a cactus here. So we got a cactus. I actually once drew a webcomic where there was a cactus as a character, believe it or not. So this is definitely in. Well, I guess it's been a while since I drew a cactus. I better stop singing that song. We'll get a copyright strike. Get my hat. Oops, I can't erase. No erasing. And we got some spikes coming out of them. I've only got one size line, so. There we go. There's your cactus with a guitar. It was like it was meant for me to draw it there. And you'll see that I have no idea. I don't know how to read music, so I think these are music notes, but I've never learned how to read music, so there you go. Ta-da! Uh-oh, Sharon and Hunter are at it again. Anyway, so tomorrow what we're going to do is we're going to try to wrap stuff up. We're going to try to talk about the contributions of what I call the three wise men, De Broglie, Heisenberg, and Schrödinger, and kind of show you how this got real weird and real mathematical. But again, it'll be a kind of a baseline understanding of our modern view of the atom. We might be a day behind the content, but thanks, Emily. Oh, jeez, what kindness. So we might be about a day behind. Just keep up with the video quizzes. And again, if you have any questions, ask me in the email. Google Hangout, please contact me. You are missed. Continue your social distancing. Maybe prank someone today, but not inappropriately. There's definitely some inappropriate pranks. Oh yeah, before I forget, I did put, I would definitely check out the link in the description. It is probably the best explanation of bright line spectrums that I've ever seen. So a lot of you are not clicking on my enrichment links. I can tell because I put some pretty good links in there and no one has said anything about them. But today's link is outstanding. It's really the best bright line spectrum I've ever seen. So anyway, that's it. Hey, listen, it was great to see you guys. Well, not see you, but it was nice to see you chatting. And we'll pick it up here tomorrow. Thanks for watching. Ask me questions if you have any questions about the end of the quarter. And have a great day.